So let's take a look now at an example problem for Module 12 for ME 270 Structural Dynamics. So in this example problem here, we're looking at is a 2 degree of freedom system. We can see this down here in the figure below. This is going to be a spring mass dashpot system with harmonic excitation. So they give us the fact that our P1 of t is equal to capital P1 times the cosine of our omega t. And we have the fact that K is given to us as 987, K prime is 217, our M is 1, and our C value here is given to us as 0.6284, and our C prime here is given to us as 0.0628. And they want us to determine the system's natural frequencies F1 and F2 and the corresponding mode shapes Th1 and Th2. Now we're just solving part A of this problem. There is a part B, C, D as well, but we're just going to be solving part A, and we're going to simplify it down a little bit. And I want to take the time to go through some of the detail in the initial parts of setting this problem up in order to solve for these natural frequencies and the corresponding mode shapes. So the first thing I want to do once I've read through the problem statement is to take a look at everything that's given within the diagram and the wording of the problem, then create my setup page. So on my setup page here, I have the title of the problem. It's for ME 270, and this is a 2 degree of freedom system here. Now the given information in this, I'd like to write all in one spot over here on the left. This is all my given information that I can reference back to. So my P1 of t is equal to P1 times the cosine of omega t. My K is equal to 987. My K prime is 217. My M is equal to 1. And my C is equal to 0.6284. And my C prime is 0.0628. I have my given diagram I've redrawn over here. Got my two masses, M and M, and I have my K value here corresponding to this spring constant, my K prime to this spring constant, and a K here for this spring. I have my damping constant C, C prime, and C here corresponding to those dampers, and I have my displacement here, U1, and displacement U2. Now they want us to determine the system's natural frequencies, which is our F1 and our F2, and also to determine our corresponding mode shapes, Th1 and Th2. So now that we've taken the time to read through the problem statement, understand exactly what they're giving us and what we need to solve for, then we've created our setup page. So we have a place we can go back to reference all those given values and what we're solving for at the end of the problem. Our next step is to begin our solution. And again, when we begin our solution here, what I want to do is focus on everything that I need to solve for. What do they ask us to solve for in this problem? Well, they asked us to solve for frequency and mode shapes. Now, I noticed the response from a lot of students was that everybody had a hard time of knowing where to start with the problems, how to begin solving them. So what I'm going to do is focus in this problem is how we do exactly that. So the first thing we want to do is come up with a governing equation. Now, this one here, I'm going to look at for my governing equation is my complete equation of motion. So even if I don't need the complete equation of motion, it's a great spot to start, and we can simplify it down as we move on. So that's exactly what we do here. Here's my complete equation of motion for part A for my solution here. And again, we're just solving part A. Part B, C, and D was a similar problem in the lecture slides that cover the entire solution for the rest of those parts, but I want to focus just on getting the problem set up and take the time to look at the details there. So for our complete equation of motion, we have our mass matrix here, 2 by 2 matrix for our mass matrix. We have our acceleration, or our U double dots. We have our damping constant here in this matrix. We have our U dot right here. We have our spring constants in this matrix, and we have our U right here, and this is equal to over here on the right, our P of t. So to simplify this down for our problem here, first thing I want to look at is my undamped free vibration equation of motion. Now, undamped, let's think about what that means relative to our complete equation of motion. Well, undamped means there's not any damping going on, so we can eliminate our C portion of this equation here. So therefore, our equation of motion in matrix form now simplifies down to this right here. We have our mass matrix, our U double dot, our spring constant matrix, our U is equal to 0 over here. So we can also know that there's some substitutions here in order to get our omega terms in. So the next thing that we want to do is take a look at what we're calling our algebraic eigenvalue equation of motion here. So what this is here is now a simplified version here where we have our spring constant matrix here, our K's, and this is for our problem here. So this, you can see, is a K plus our K prime, a negative K prime, K plus K prime there, minus our omega squared term now, times our mass matrix right here, times our mode shapes Th1 and Th2 is equal to 0, 0 here. So we can multiply this through by our omega squared here, and we end up with, now as we have our K matrix stays the same there, minus we distribute our omega through here is omega 1 squared m and omega 2 squared m there as we distribute that through. Now we can do some matrix subtraction, say this element minus this element. Our k negative k prime minus 0, our negative k prime minus 0, our k plus k prime minus our omega squared m. So we do that out here, and we end up with this matrix down here. So now we've done some matrix subtraction. We have k minus k prime minus my omega 1 squared m minus, over here the other element here is minus our k prime. Then down here for this element is a negative k prime. And over here in the bottom element here is our k plus k prime minus omega squared m. This is equal to 0, 0 here. So now we're going to take the determinant of this matrix in order to solve for omega squared. So there's multiple ways that we can do this, and especially as we get to larger matrices, 3 by 3, 4 by 4, 5 by 5, we keep going, taking that determinant becomes a little bit tricky. And we have the question of, do we really want to solve this out by hand and take all the pages of notes? And not only that, by doing it by hand, we also take the risk of dropping a negative, losing a value somewhere, just human errors, we're writing it down. So this is where we have to ask ourselves, okay, do I want to take the time to set this up in a numeric solver? You can do it in Excel, you can do it in MATLAB, Mathematica, Python, there's all types of options. I would recommend either Excel or MATLAB, preferably MATLAB with something like this, but there is the option of doing it by hand. So just something to think about as we get to some of these larger matrices, we need to do some matrix math and take determinants. So from this one here, if we take the determinant here, we can solve for our omega 1 and our omega 2 squared. We end up with omega 1 squared is equal to our k over m when we take the determinant of that matrix, the 2 by 2 there, and solve for our omega. And our omega 2 is equal to k plus 2k prime over m, where now we can go back to our setup page. And if we go back to our setup page here, we can see, okay, k is equal to 987, our k prime is given to us as 217, and our mass is equal to 1. So we can plug those values in there, and we plug those values in, we can get numeric values for our omega 1 and our omega 2. So we can say, okay, omega 1 squared is equal to our k over m once we took that determinant and solve for that. And we can plug in, okay, my k value here is 987 and my m value here is 1. So 987 over 1, my omega squared is 987, or take the square root of both sides, and omega 1 is the square root of 987. So therefore, take that square root, and omega 1 is equal to 31.42 radians per second. Now we do the same thing for our omega 2. We can say our omega 2 squared is equal to a k plus 2k prime over m, where k is 987, our k prime is 217, and multiply that by our 2 from this equation there, and put it over our mass, which is equal to 1 right there. We end up with omega 2 squared is equal to 1421. Take the square root of both sides, and omega 2 is equal to 37.7 radians per second. So with those values now, we can go back to our eigenvalue equation that we derived earlier and start plugging those values in. So we have this general matrix up here. Now we have two values of omega 1 and omega 2 that we can plug in for either of those. So we'll solve for one at a time when we plug in for our omega squared right there. And our k matrix, again, we recall, was k plus our k prime minus k prime minus k prime, k plus k prime there. We have our m matrix there. We have a value for m, have a value for k prime, and have a value for k. So we can plug all of those in. So when we do that, what we end up with for our k matrix is 987 plus 217, negative 217, negative 217, then 987 plus 217. And then we have a minus either our 987 or our 421, depending on which value we want to plug in first and solve it through, times our mass matrix. We put our m's in as 1, and then we can solve this here. So I'm going to choose the top one here. Let's just go with 987 first, my initial value I solved for my omega 1 there. So plug that in. Do up my math here. My 987 plus 217 becomes 1204. This is negative 217, and this is 1204 as well. Times when I multiply through by my 987 by omega squared, this is my new mass matrix with the omega squared multiplied through. And now you can see what I don't have here is my Th1 and Th2, so I can do a little bit more matrixy math in order to back out my mode shapes. So I rewrite that out up here. Have my initial k matrix here, my omega m There's my mode shape right there is equal to 0. So I can subtract these two right here, do a little matrixy math, and this is 204 minus 987. Sorry, 1204 minus 987. Then this is negative 217 minus 0. This is negative 217 minus 0. And this is 1204 minus 987 there. Times now my mode shape Th1, Th2 right there is equal to 0. Do out the subtraction within this matrix, end up with 217, negative 217, negative 217, and 217 there, times Th1 times Th2 is equal to 0. Well, I can do also matrixy multiplication now there, and I end up with 217 Th1 minus 217 Th2. Then we have a minus 217 Th1 plus 217 Th2 is equal to 0. So I can do that out there, two equations, two unknowns there. What we find out when we reduce and simplify this is that our Th1 is equal to Th2. So if we let Th1 is equal to 1, it makes 217 equal to 217 there. That checks out right there. So Th1 is equal to 1, and Th2 is equal to Th1, which is also equal to 1 there. Now we can do the same thing, but plug in for our omega 2 squared. So omega 2 squared was 1421. So we plug that in here. So this is our same K matrix here. Nothing changes. So I'm going to go back right to where we were before, 1204, negative 217, negative 217, and 1204. But now I'm plugging in my 1421 here for our omega squared value there, times my mass matrix of 1001, times my mode shapes there. Plug this in, distribute this omega squared through my mass matrix. When I multiply that through, I end up with this 1204, negative 217, negative 217, 1204, minus now my omega squared times my mass matrix here, 1421, 1421 there, times my mode shape, Th1 and Th2 is equal to 0, 0 there. So therefore, now I can do some subtraction, matrix subtraction, my 1204 right here minus my 1421 ends up being negative 217. Negative 217 minus 0 is negative 217. Negative 217 minus 0 here is still negative 217, and 1204 minus 1421 is a negative 217. So now I have a 2 by 2 matrix that's all negative 217 there, times my mode shapes, my Th1 and my Th2 here is equal to 0. So this ends up, when I do the matrixy math there, multiply through in the right order, I end up with negative 217 Th1 minus negative 217 T2, and then negative 217 Th1 minus 217 Th2 is equal to 0, 0 there. So I do this out here, and I see that negative Th1 is equal to 2, or Th1 is equal to negative Th2 there. So our Th1 is equal to 1, and our Th2 is equal to negative 1 there. Therefore, for my mode shapes, I have this value here, Th1 is equal to 1, 1, Th2 is equal to 1, negative 1. And that's as far as I'm going to take this problem here, is just up to our mode shapes. And from our mode shapes, the next thing that we need to solve for is our frequencies. So those are the two things in part A that they wanted us to solve for, is our natural frequencies in hertz. So again, then pay attention to that, and those mode shapes. So for our natural frequency in hertz, we can simply do our conversion here. That frequency in hertz is equal to our omega, our natural frequency, divided by 2 pi. We've already solved for our omega 1 and omega 2 within this problem here, so I can plug directly in there. So frequency is equal to omega 1 over 2 pi, which is equal to 31.42 divided by 2 pi. So F1 is approximately 5 hertz. For F2, I take my omega 2 over 2 pi, or 37.70 radians per second divided by 2 pi, and my F2 is approximately 6 hertz.